Do you see my screen now? Yes?
Yes.
Okay. So we learned the main principles of routing algorithms by looking at different approaches. Now we are ready to study the most common routing protocol that are utilized in the internet. And more specifically, we're going to talk about RIP, OSPF, as well as the BGP. Let's start with the RIP. Well, of course, before that, let's give some background information about these three protocols. So remember, we talk about the AS, autonomous systems. We have an inter-AS and we have intra-AS routing protocols. This intra-AS within the AS routing is also known as interior gateway protocols, which stands for IGP. So most common intra-AS routing protocols are RIP, Routing Information Protocol, OSPF, Open Shortest Paths First, and IGRP, Interior Gateway Routing Protocol, which is owned by Cisco as a proprietary solution. So let's start with the RIP. And this was included in the Unix distribution in 1982. Is based on the distance vector algorithm. Remember, guys, we just learned. Distance matrix, number of hops, maximum it can support is 15 hops, and each link has a cost of 1. And distance vectors are exchanged with neighbors every 30 seconds in response message, also known as advertisement message. In each advertisement message, you can list up to 25 destination subnets. And this is a typical kind of from router A to destination subnets. And that shows the number of hops from U, 1 hops from for the subnet of V is 2 hops, for subnet of W is 2 hops, and so on. Let's give an example for the RIP. We have the nodes and the routers A, B, C, D, and we have the subnet X, W, Y, Z. So this is the routing table in router D. And the first column is the destination subnet. The second column is next router. And the third column is for number of hops to destination. So as you can see, for the destination subnet, in order to reach from D to the subnet W, the next router is A, and you reach 2 hops, right? And for the subnet Y, in order to reach from router D to the subnet Y, you go through the next router is B, and the number of hops is 1 and 2. And for the Z, you go through the B, next router is B, and there is 7 hops to reach to this destination. I assume that there's an update through the advertised message from A to D, router A to router D. It's saying that, as you guys see, there's updates in terms of destination Z. You can reach to the Z subnet through the router C, and the number of hops is going to be 4. Compared to the 7, 4 is much less, right? That's why we need to update this table in router D for the Z subnet. So now I update it. In order to reach to C, I need to go through A. Next router is A, and the destination is 1 plus 4 is equal to 5. So that's why That's how I update the routing table in router D if I receive an advertisement message. So in terms of how the RIP manage the link failure or recover a link. So first of all, if there's no advertisement heard after within 180 seconds, means 3 minutes, right? And the protocol is gonna declare that this neighbor link is dead. So it routes via neighbor invalidated and new advertisements sent to the neighbors about this failure. The neighbors in turn send out new advertisement if tables change, of course. And link failure information quickly propagates to the whole network. And the poison reverse method is used to prevent ping pong loops. So ping pong loops are prevented using the poison reverse method. RIP table are processed, and so let's look at RIP table processing. The RIP routing tables are managed by the application process called routd, or it's called daemon. So at the application layer, we have a process called routd. In other words, a daemon. So this application layer process, it manage this forwarding table at the network layer. So that was the information about the RIP, which was a distance factor algorithm. Now let's look at the link state algorithm, which is OSPF. And the open term in this case means it's open source, kind of publicly available. It uses link state algorithm. It utilizes the link state algorithm. So you need to disseminate the link state packet. And in the link state, each node has a topology map. And we compute the route using the Dijkstra algorithm that we learned. And OSPF advertisement message carries 1 entry per neighbor, and the advertisement is flooded to entire AS. So this is carried in OSPF messages directly over IP, rather than using the TS, TCP, or UDP. It's put on top of the IP. There's another. It's called IS routing protocol. It's very close to, very identical to OSPF. There are some advanced features that are not in RIP. One of them is the security. In OSPF, all the OSPF messages are authenticated so that we can prevent the malicious intrusion threats. Multiple same cost paths allowed. In IRP, only one path allowed. In this case, multiple same cost paths allowed. For each link, multiple cost matrix for different TOS. Integrated uni and multicast support. So the multicast OSPF, which is called MOSPF, uses the same topology database as OSPF. And we use the hierarchical OSPF in large domains. Let's look at the hierarchical OSPF that are utilized in the large domains. First of all, we split the network into two parts. Is the local area part, this part, or the local area part, and the remaining blue region is called backbone. And we have different types of routers in this case. In the local area, we have the internal routers you see. And then at the root of each local area, we have area border routers that are connected to backbone router. And all these backbone routers connected to the boundary router. that talk to the outside of this network. So as I mentioned, two level of hierarchy, local area backbone. In this case, link state advertisement only in area, and each node has a detailed area topology. Only know the directions to the networks in other areas. And the second one of another type of routers, it was area border, remember? Summarize the distance to the networks in own area, and it advertised to other area border routers. And then these area border routers, they are connected to backbone routers. These backbone routers, they run OSPF routing limited to the backbone. And finally, at the top, we have the boundary routers that connect to other autonomous systems. So let's look at the inter-AS routing protocol that is utilized in Internet, which we call BGP. BGP stands for Border Gateway Protocol. This is the de facto inter-domain routing protocol. It's actually the protocol that holds, that stick all this internet together like a glue. So BGP provides each AS a means to. There are two types of BGP. eBGP, external BGP. It obtains subnet reachability information from neighboring AS. It's responsible to obtain subnet reachability information from neighboring AS. iBGP is the internal BGP. It propagates reachability information to all AS internal routers. So it determines the good routes to other networks based on reachability information and policy. So it allows subnet to advertise its existence to the rest of the internet by saying, hey, I am here. Let's look at the BGP basics session. Two BGP routers exchange BGP messages, of course. Advertising paths to different destination network prefixes and exchanged over semi-permanent TCP connection. So when AS3, for instance, advertises a prefix to AS1, AS3 promises it will forward datagrams towards that prefix. AS3 can aggregate prefixes in its advertisements. So distributing path information. And remember, we have two types of session, eBGP session, which is the external BGP session that is utilized between AS. iBGP is a session that is utilized within a single AS. So using eBGP session between 3A and 1C, as you see, eBGP connect 3A and 1C. AS3 sends prefix reachability information to AS1. Through this link, we send the prefix from AS3 to AS1. 1C can then use iBGP. Then after that, 1C needs to distribute this prefix into all routers within AS1. 1B, let's say 1B receive this prefix information, and 1B can then re-advertise new reachability info to AS2 over 1B to A, to another AS, like 2A in the AS2. So when router learns of new prefix, it creates entry for prefix in its forwarding table. So distributing path information, so we use the prefix. What's the route? So we are talking about router, route. What's the route? Route is equal to prefix plus attributes. So when we advertise prefix, it includes the BGP attributes. So there are two important attributes. And as an autonomous system path, it contains AS through which prefix advertisement has passed. It shows, which prefix advertisement has passed. For instance, as it passed through AS67, AS17. Next hop, it indicates the specific internal AS router to next hop AS. So in order to show a specific internal AS router to next hop AS. Gateway router receiving route advertisement uses import policy to accept or decline. For instance, it can say never route through this AS X. Is a policy-based routing. So BGP route selection, the router may learn about more than one route to destination AS. So it selects one of these routes based on four criterion. First, the local preference value attribute, which is based on policy decision. Then shortest AS path. Then closest next hop router using the hot potato routing. And then you can add some additional criteria. So BGP messages, it can be exchanged between the peers over the TCP connection. And BGP message can be like open, update, keep alive, notification. You can see the explanation of each of these messages. So putting all this together, how does an entry get into the router's forwarding table? So answer is complicated, and we need to look at other section. So assume prefix is another AS, and we have such entry. Okay, let's look at the steps. Router becomes aware of prefix. Router determines the output port for prefix. Remember here, we have this prefix, and the corresponding output is 3 in this case. Then the router enters the prefix port in forwarding table. So router becomes aware of prefix, the first step. BGP message contains the routes. So what was the route? It was equal to prefix plus the attributes, as you guys remember. And the attributes are as paths and next hop. Just give an example. What's the route? So is the prefix this IP address with the subnet address, and the attributes AS path that shows which this message has passed through. So it is going to pass through AS3, AS131, and the next hop is going to be this router IP address. This is the route, an example for a typical route. I'm skipping this part. So you can come up with multiple route, and the router selects route based on the shortest AS path. For instance, I have two routes. Let's say the first one is AS2, AS17, and the same subnet. AS3, AS131, AS201, and same subnet. The difference is in this route is going to pass through 2 AS. In this case, is going to pass through 3 different AS. So I should select which one? The shortest AS path, which has 2 AS. So find the best intra route to BGP route. We are going to use the selected routes next hop attributes. Routes next hop attribute is the IP address of the router interface that begins the AS path. Example, this is the AS path AS2, AS17. The next hop is this IP address, like an IP address of a router in AS2. So the router is going to use OSPF to find the shortest path from 1C router to that specific 2A router. So the router identifies port for route. How we are going to identify the port along the OSPF shortest path? We add this prefix port entry to its forwarding table, like this subnet, and then we add the port number 4, router port. How to put the routing? Suppose there are 2 or more best inter routes. Then we are going to choose route with the closest next hop. So use the US OSPF protocol to determine which gateway is closest. And from 1C, for instance, choose AS3, AS1, 131, or AS2, AS17. So we select the route AS3, AS201 since it's closer. So to summarize how we enter the entry into the forwarding table, first, router becomes aware of prefix. Via BGP route advertisement or from other routers, we become aware of this prefix. And then determine the router output port for prefix to direct. And use BGP route selection to find best inter-AS route. Use OSPF to find best intra-AS route, leading to the best inter-AS route. And router identifies router port for that best route. And then enter the prefix port entry in the forwarding table. So we said that the BGP is based on policy. Let's look at the routing policy. In this network, we have 3 internet provider, service provider networks, A, B, C. And then we have 3 customer, X, W, Y. So X is dual home. That means it gets an service from B and C providers. So that's why X doesn't want to route from B via X to C. So X will not advertise to B a route to C because it's a dual homed. You put the policy, the rules based on your organization requirement. For instance, A advertises path AW to B. B advertises BAW to X. Should B advertise this path BAW to C? No, because B gets no revenue from this routing. Because neither W nor C are B's customers. So B wants to force C to route to W via A, right? B wants to C to route W via A. So because C is connected to A, why it should route X and then B and then A and then W. So B wants to route only to or from its customers. Why different intra and inter-AS routing? It can be based on policy because inter-AS admin wants to control over how its traffic routed, who routes through its network. Intra-AS single admin, so no policy decision needed in this case. So policy is usually is based on inter-AS routing. When we look at from the scale perspective, the hierarchical routing saves table size and reduced update traffic. When it comes to the performance, intra-AS can focus on the performance. Performance is important for the intra-AS. For the inter-AS, policy may be more important than performance. Okay, guys, that's all for today. Any question?